In our first class, we saw a block diagram and we talked about the ability of feedback to help control systems. We're finally coming back to that now that we've essentially taken a hiatus and kind of reinforced our mathematical and some of our engineering toolboxes. So now we're coming back to it, and it makes sense to kind of sit and again go through each of the pieces that's included in a generic feedback diagram and a feedback control system, and then also look at the goal of what we want to do from a couple different perspectives, because we're going to look at what goal we want, what we want our controller to do, and that's going to be dependent a little bit on the different scenarios that we consider. So if you remember, we've spent a lot of time so far talking about the process dynamics. So we've been talking about the open loop system. So essentially we've been focusing on just this one block. But fortunately, the tools that we've been developing, essentially Laplace transform tools, the like final value theorem and initial value theorems from Laplace transforms, talking about step responses and other kind of responses. I'm talking about the Bode plots that characterize frequency domain information. All of these are going to be relevant because they're relevant for a transfer function. And similarly, our state space tools will continue to add on to those and to reinterpret what we already know. But the idea is that those describe a system, and in that case, it was simply the system was just the process dynamics. But now we're going to zoom back out, and now we're going to see the entire feedback diagram, and that is the whole system. And what we're going to show, and that's what we're going to work on right now, is how we can characterize this whole feedback loop as a single transfer function, or as a specific system. So again, we have process dynamics. That's kind of one of the hearts of what we're doing. Out of the process dynamics, we take a measurement. That's our output. That output could be corrupted by some amount of noise. And so we're going to talk about noisy sensors. And so we're consider that kind of noise. In order to design the input, so the input is U, and in order to design that, we use a feedback controller. So a feedback controller, different than the open loop one that we talked about in the last set of videos, is that it employs this output in its effort to control the system. So this input, that input could get corrupted or could get disturbed by other signals. These could be forcing factors, physical forcing factors, could be different kinds of uncertainties, but other signals that we're going to lump into disturbances get added on with the input, and those get put in as the input into our process dynamics that then produces the output. So now we're all about how we're going to design this feedback controller. And the way that we're going to do this is we're going to, motivated, again, if you think back to our cruise control example, we have some desired reference that we'd like our system, meaning our output, to look like. So if we specify that this should be 70 miles an hour, we want y of t to become 70 miles an hour. It's certainly possible that instead of a static value, this could be something that changes over time. And so you could imagine that like a cruise control or an autopilot, say on a plane, its reference trajectory could be something that changes over time depending on weather, depending on plane characteristics, and so on. So we can understand that the reference could be something that that maybe could change over time. So we're going to be comparing the reference with the output, and so that's what this minus sign does. It constructs the error, and that error is simply just r minus y. And so that's why we have a sum here. This comes in with a plus sign. This is minus y, and this is this is essentially r. However, it could get permuted by this reference prefilter. And so this is a little abstract to understand what that means right now, but the idea here is that essentially we're going to do a transformation, and so this wouldn't exactly be r anymore. This would be some transfer function here multiplied by r. So if you gave this the letter, say P, this would be P times R. Um, and the role that this could play is the fact that perhaps it could be a unit conversion. For example, we specify a reference in miles per hour, but somehow that needs to get translated into, for example, information about the engine, which could be, for example, based on RPMs. So that could be essentially converting from miles per hour to RPMs. And so that would be the role that this reference prefilter would take. But oftentimes we don't have that term, and so we're simply just sticking in the reference. And so again, you can kind of think about the error as simply a reference minus the output. And that error is what gets fed into the controller that produces then the input U. So so that's the big picture. And if you think about what's being specified, we have a signal that's being specified, that's the reference. We have a signal that we don't get to control, that's our disturbances. And we have a signal that is the sensor noise. And so we have all three of those terms. And like the open loop case, we have these three terms, and we're interested in understanding how feedback helps us with our ultimate goal, which is how does this combined controller make the output track the reference? So we know that Y maybe can't be exactly equal to R, but we'd like for Y to kind of approach R and track it is the terminology that we'll continue to use. So this is the big picture. This is the most general case that we'll take a look at. And so now what we're going to do is we're going to take a look at a few specific examples that really helps us understand what the role of each individual piece of this feedback control loop is. All right, so if we remove a few terms, in particular we remove the reference, so we set the reference to be 0, then we can kind of interpret that this more simplistic feedback loop, the goal is to design a controller that produces an input that makes Y go to 0. So we'll call that stabilize Y. And so instead of making Y track the reference, we're making it track 0. One of the ways to think about that is simply just the fact that the reference is 0, so we're trying to still track the reference, it's just that the reference is 0. So in that case, again, we're designing this controller to produce an output that is robust to disturbances and robust to noise. And in addition to that, this process could be either stable or unstable. If the process is stable, then then a lot of our job's already done, but it's possible that we would like to make it more stable. But if it's unstable, then stabilizing the output is the main goal of that feedback controller. So again, another way to interpret, because we're going to see a lot of feedback diagrams that look like this, especially at the beginning, without a reference. And so it's interesting just to think about this as now as a stabilizing feedback controller. If we simplify this one more step and essentially get rid of noise and we get rid of disturbances as well, now this is really just a system that's meant to stabilize, building a controller to stabilize the output. And here, if the process is already stable, then again, most of our job is already done. This is particularly interesting when we want, when this is an unstable plant and we'd like to make sure that it becomes stable. And so the key takeaway in simplifying all of this is the fact that making Y track R, so that original control goal of making the output track the reference, is equivalent to making the error track 0. Or namely to what we used on the last slide, stabilize the error. So tracking the output tracking the reference is the same thing as stabilizing the error, because essentially the error, right, we wrote that as R minus Y. So if we stabilize the error, that means the difference between R and Y goes to 0. And so that is what allows us to track that. So if you go back to the slide 2 slides ago, remember that in the context of the reference, when we had a reference coming in, we had a sum, and then this came in with a minus sign, essentially. And here, the idea is that the thing that's feeding into the feedback controller in that more generic diagram is the error, right? And so now, if we get rid of that reference, then the thing that's being fed back here, that thing that we're trying to stabilize, is just y. So that's why I said that in this context, we're just stabilizing y. But in the more general context, we're making y track r, and the way we do that is by stabilizing the error, e. All right, so this slide is meant to be very similar to the open loop slide. So as we go through this, if this becomes confusing, it's worth to go back to what we talked about in terms of open loop control and deriving our transfer functions that correspond. In that case, it was an open loop system. We didn't have this feedback part down here, but now we do. So what we'd like to do is we'd like to understand how the three different factors, these input signals, affect the performance of our output. So in order to do that, we're going to go ahead and write down the transfer functions. And ultimately, what we're interested in understanding is how does the output, how is it being driven by these three different separate inputs, those different input signals. So what we're going to do is we're going to write y, and we're going to write y as g, as the output of g times its input. And its input is just u and w together. So y is equal to the transfer function g multiplied by its input signal, which is u plus w. So w is an independent input, but what is u? So u is the output of this controller, which takes its input. So let's call this temporarily, let's call this this E, that's the error that's getting fed into the controller. So that means that U would be equal to K times E. All right, and now what is E? Let's look at E. E is simply just this sum, it's specified by this sum. So that would be R plus R, and down here minus what comes in on this edge is the combination. So if we look here, it's y, that's coming down here, plus v. So this signal right here, y plus v, is on this edge, and that gets fed back in here. So that's subtracting away y plus v. All right, so if we were to substitute E into here, that gives me U, which is K times R minus the quantity y plus v. And then we have our disturbance out here. And so expanding that out, so just multiplying that through, we get these terms. And what we notice is in the context of feedback, and this is because of feedback, we have a y term on the left-hand side and we have a y term on the right-hand side. And so we're going to combine those together over here on the left-hand side, leaving three remaining terms on the right-hand side, and then we're going to solve for y. So now we want y as a function of those three inputs. So we're going to divide by this 1 plus gk, and that gives us three transfer functions that represent how each of these different input signals affect y. So this gk over 1 plus gk, that is the transfer function of that relates the output to the reference. And minus gk over 1 plus gk, that's the transfer function that relates the output to the sensor noise. And same for disturbance. So just as before, we're interested in making y track the reference. So that means that we would like this transfer function to be very, very close to 1. And we'd like these transfer functions to be very, very close to 0. And so what's interesting now, if you compare what we got in the open loop case, the open loop control case, these last two terms did not have anything to do with the controller K. But what you'll notice now is that the controller K appears in these transfer functions. And so now before we couldn't really do anything about the sensor noise and the disturbance, but now by implementing this feedback, we can not only change the transfer function with the reference, we can also change these two transfer functions and hopefully achieve better tracking and better disturbance rejection. And then we'll also take a look at our other properties as well. So in the spirit of interest in tracking, we're going to compose our error, which again is just r minus y. And so if you just take r minus this quantity, the only one that's affected is this first term, which is essentially r minus gk over 1 plus gk times r. So you factor out the r, and that becomes 1 minus gk over 1 plus gk times r. And if you just get a common set of denominators here, then you'll realize that you're just left with 1 over 1 plus gk for the transfer function that relates the tracking error with the reference. So again, now in the context of tracking error, now we want this transfer function to go to 0, and this transfer function to go to 0, and this transfer function to go to 0. One of the things that we'll comment on later is the fact that this transfer function, we will give that the name S, and this transfer function will give the name T, and these actually sum up to 1. So if you, again, you've got common denominators, so if you just take S and T and add them together, you notice that you get 1 plus GK on the top, on the numerator, and so that gives you unit value. So, and that's why these are called, well, we'll see in a minute why, in a couple of videos, why this is called the sensitivity function, but that's actually why this sum is why this is called the complementary sensitivity function. So again, these are the transfer functions that characterize how the three different inputs affect our output y. And so again, our goal is going to be to take a look at the 4 control goals, and that's what we're going to be doing throughout this entire sequence of classes about closed loop feedback control. One of the things that we had to do here is we had to kind of manually create this expanded expression of the system to ultimately get an kind of an input-output characterization of the whole system. What we're going to look at in the next video is some simple ways of calculating transfer functions of various different block diagram configurations that'll help simplify these calculations. So before we go, there's a very common point of misunderstanding about feedback diagrams. And part of the challenge here is that everything is essentially represented by a transfer function. So if we have a reference that is, for example, a step input, then that gets represented as a 1 over s, which looks just like a transfer function that would say describe the plant. But there's a very important delineation between what goes in a box and what goes on these wires or these edges. So when I say a signal is something that we can take the inverse Laplace transform of and get a function of time. And so that's like a sinusoid, that's an exponential. These are things that change with time. It could be constant with time, but these are time signals. So this is something, the best way to think about it is, this is something that you could measure and look at like on an oscilloscope and see it changing and varying. So something like the voltage or the current or the position, these are things that would make sense to make plots of over time. What goes inside these blocks are things that change the signals. So the controller takes in an error signal and puts out the input signal U. Just like this takes in this combined signal, U plus W, and G does a transformation on it to produce the output Y. So mathematically, this creates a transformation of the signal, whereas these, the edges, the arrows, are all the signals that are being passed around in the system. And again, the blocks are things that are changing those signals. Okay, so that's a really important distinguishing key characteristic. That's why you would never put K, meaning the controller transfer function, that would never be on a wire. And similarly, you would never put W or U, these being signals, you would never put them in a box. So that's a really important thing to keep in mind as we keep moving forward. So now we're going to take a look at the 4 different control goals and simple ways to combine block diagrams into a single overall transfer function, with the idea that what we've done in going from this block diagram with these 3 different inputs down to these expressions, this actually means that we have a single block that describes how R gets put in and what Y comes out. And what's inside this block is GK over 1 plus GK. So we have kind of aggregated, we've collapsed this entire feedback diagram into a single block. And so that's the power, because now if you look at this just right, this is nothing different than when we had an input U going into the process dynamics and producing an output Y, right? All we've done is change some letters. So this is an input, this is an input. This is a transfer function of a system, this is a transfer function of the system. This is an output, this is an output. So by spending numerous weeks now studying this kind of system, we've now prepared ourselves to study this system. Because what we've done is we've been able to calculate a transfer function that represents this whole feedback diagram and feedback system. And we've constructed that transfer function from the original system dynamics and the controller that we'd like to design. So again, that's how our tools get used now on these more complicated feedback systems.